Hello. So, in this lab, in this week, we learned about amino acid titration and the determination of PI. So, we learned the following topics were covered in this second week. We learned about the properties of amino acids. We learned that amino acids have an amino group and a carboxyl group, which gives it this acid base property. So, these amino and carboxyl groups are the ionizable groups, and we also learned that there are some amino acids which have additional ionizable groups in their side chain. For example, aspartic acid or glutamic acid, which have an acidic side chain, or lysine, arginine and histidine, which have a basic side chain. We learned about the concept of isoelectric point for amino acids, which means that a particular pH at which a particular amino acid is neutral is referred to as its isoelectric point. We learned that this PI isoelectric point can be determined using amino acid titration, and we saw two in-lab experiments where we determined the PI of glycine and lysine. So, I will just quickly go over the concepts that we have learned in this week and try to show you the important points. So, here is a very basic setup of a titration experiment, and we saw that being performed in the lab. So, what we wanted to do is we determine the PI of an amino acid. So, what we did was we made a solution of an amino acid. For example, first we used glycine. So, a glycine solution 0.1 molar was taken in a beaker, and we titrated it with a base. We took sodium hydroxide, which was roughly around 0.5 normal. To start the titration experiment, we want to span a whole pH range. So, what we did was we dropped the pH to a very low value. To do that, we used hydrochloric acid. So, we added hydrochloric acid to the glycine solution and dropped the pH below 2, and then we started our titration experiment. So, the titration experiment was done by drop wise addition of sodium hydroxide to this amino acid. It was thoroughly mixed by stirring, and the pH at each, after addition of each drop, was measured using a pH meter. So, we got two readings. One is the pH after addition of each drop, and from the volume of each drop we also determined how much sodium hydroxide we are adding at each titration point. So, this can be very nicely plotted in a graph like this. So, the x axis is the amount of sodium hydroxide that is added. So, here I am writing it in terms of millimoles of sodium hydroxide, and in the y axis we can plot the pH that we measure at each titration point. So, if we do that, it will look something like this. So, each of these points are the titration points, and what you will see here is that during titration the pH was initially increasing in a linear fashion, and suddenly here the pH jumps. So, it increases a lot by just addition of 1 or 2 drops, and then again it stabilizes and it increases linearly till we reach the end of the titration. So, we can join these points and get a nice titration curve like this. So, what are these different regions of a titration experiment? So, if this was glycine, so this titration curve is actually shown for an amino acid which has only 2 ionizable groups. So, for example, let us say if this is glycine, then one ionizable group is the amino group, and then the other ionizable group is the carboxyl group. At very low pH in this region, glycine will be in this form, where the carboxyl group is protonated and the amino group is also protonated, which means that the glycine amino acid will have a net positive charge. As we keep on increasing this the amount of sodium hydroxide, the pH will increase, and at this point we get an inflection. So, that inflection is due to the ionization of this carboxylic group. Okay. So, the carboxylic group loses the proton somewhere here, and if you draw a straight line and take the midpoint of that straight line, you will get the pKa value, which will be the pH at this midpoint. So, that pKa value will be for the ionization of this carboxylic group. So, that will be your pKa 1. Then the pH suddenly jumps and again we have another straight line, and here this second group is getting titrated. So, it is losing its proton, so that the amino group now becomes neutral. So, for this transition we get this straight line. So, if I draw a straight line here and take that midpoint, the corresponding pH will be the pKa for this transition. Okay. So, one pKa will be here, another pKa will be here, and my pi will be somewhere in between that, which will be the midpoint of this transition point. So, at that pH the species will be mostly in this form, where we have a single positive ion and a single negative charge. So, positive charge, negative charge gives you a neutral species. So, that will be the pi for glycine. Okay. If we look at the actual data, so this is the data from the experiment that was performed in the lab, and what I have done is I have plotted the millimoles of NaOH and the pH that was recorded by Pritam when he demonstrated the titration of glycine. So, to perform this experiment, he used 10 ml of 0.1 molar solution of glycine. He used 0.635 normal HCl to lower the pH below 2. So, you will see that we are starting somewhere just below 2. This was roughly around 1.8, and then he performed the titration using 0.714 normal sodium hydroxide. He added it dropwise and measured the pH. So, as he added sodium hydroxide dropwise, the pH changed in this fashion. So, this is very similar to the titration curve that we saw in this slide, except in this region there is something else is happening. Okay. So, this is something that you will notice for all experiments, that they will not look exactly like this idealized curves. Okay. So, it will deviate at some point, and it depends on experiment to experiment, but we can use this data. So, if you can see that this is the first linear region, and if we draw a straight line here, we can determine the midpoint of that straight line somewhere here. So, that will be our pKa 1, and this is the second linear region, and if we draw a straight line here and get the midpoint, our second pKa will be here. So, if I do that, I will get pKa 1 and pKa 2, and this value roughly comes out around 2.3, and this is around 10.2. So, if I take an average of these two pKa values, I will get the pi for the glycine from our titration experiment that was performed in the lab. So, 2.3 and 10.2, you add them, divide them by 2, you have your pi. So, here this was again discussed in the lab, but I am just summarizing some of the important points. We did not make a standard NaOH solution. We actually made a NaOH solution, and then we titrated it with oxalic acid to determine the strength of the NaOH solution. The reason we cannot make a standard NaOH solution is because sodium hydroxide is very hygroscopic, it absorbs moisture. So, when you take out sodium hydroxide pellets from your beaker or bottle, wherever it is stored, and weigh it, you do not know how much of that weight is actually sodium hydroxide and how much is moisture. So, you have to determine the actual amount of the number of moles of sodium hydroxide that you have in the solution by titrating it with some primary standard. So, in this case we used oxalic acid. The reason oxalic acid is used is because it is non-hygroscopic, so it will not absorb moisture, it can be handled very easily, and it is also not very costly. So, we used a standard solution of oxalic acid to determine the strength of sodium hydroxide, and phenolphthalein was used as the indicator. Once we know the strength of sodium hydroxide, we use that to standardize the hydrochloric acid solution. The pH meter were calibrated using standard buffers that was provided. Again, this is very important, because if your pH meter is not calibrated, then again your reading will not be very reliable. We used this standardized HCl to lower the pH of our amino acid to a value which was less than 2, and then we used sodium hydroxide from the burette added it dropwise, stirred and recorded the pH at each titration point. I showed you the plot of the pH versus millimoles of sodium hydroxide, and then I also showed you how we determine the pKa values, and once we know the two pKa values for glycine, we determine the Pi from the pKa values. This is the calculation that was used when the standard solutions were prepared. So, oxalic acid 250 ml 0.2 normal oxalic acid was prepared, and here the molecular weight is given. So, based on these volume that you need and the amount and the strength that you want to make, we can calculate only 2.25 grams of oxalic acid was required. So, it was weighed out, dissolved in 250 ml of water to make the standard solution, and then that standard solution was used to standardize sodium hydroxide. Our aim was to make 0.5 normal sodium hydroxide. Molecular weight of sodium hydroxide is 40 grams, and we want to make 250 ml of sodium hydroxide. So, if we weigh out 40 grams, then that will be enough to make 1 normal 1000 ml. Okay. So, this is 1/4 of 1000 ml. So, 40 by 4 will become 10 grams, but then that will give us 1 normal. This is 0.5 normal. So, you again divide it by 2. So, 10 by 2 is 5 grams. So, you need only 5 grams of sodium hydroxide. So, 5 gram of sodium hydroxide was dissolved in water, and then that was used to titrate with oxalic acid. So, this is the final result. The volume of sodium hydroxide that was required was 2.8 ml. 10 ml of oxalic acid was used, and the strength of oxalic acid was 0.2 normal. So, using this volume multiplied by strength of one species equals to volume multiplied by strength of the other species, we can figure out the strength of sodium hydroxide. So, V1 is 10 ml, S1 is 0.2, V2 is 2.8. So, we can solve for S2, and it turned out to be 0.714 normal. Similarly, using this sodium hydroxide solution, we determined the strength of the hydrochloric acid. So, we prepared 0.635 normal of hydrochloric acid, which was used to drop the pH of the amino acid to less than 2. This is the titration curve of lysine. So, again you can see that lysine has 3 ionizable groups, the amino group and the carboxyl group, and then again another amino group in the side chain. So, instead of drawing all the carbons, I have just represented it like this. When the pH was very low, you see the pH was again close to 2 or maybe slightly less than 2. Lysine will be in this form where the carboxyl group is protonated and both the amino groups are protonated. So, this species has a net charge of +2. The first titration occurs for the carboxylic group, where it loses its proton and it becomes negatively charged. So, now this has a net 1 positive charge, because +1 +1 -1. So, the net charge is +1, and this transition is given by this straight line. So, a straight line here, midpoint of this straight line will be pK1, which corresponds to the first transition or the first titration. Okay. The next species is where this backbone NH2, backbone amino group loses its proton. So, this NH3 plus becomes NH2, and this transition is given by a straight line from here to somewhere here. Okay. So, if I take a straight line from here to here, if I take the midpoint, then my pKa for this transition is somewhere here, and that comes out close to 9, between 8 and 10. The third titration is this one where the side chain loses its proton. Okay. And that is given by this other part of the straight line, and if I take the midpoint, it will come somewhere here. Okay. So, if I draw point out these 3 pKa values, pKa1 is for the carboxylic acid, pKa2 is for the amino group and pKa3 is for the side chain amino group, right. Now, the neutral species is this one, because it has one positive charge and one negative charge. So, we get this neutral group by titration from here to here and here to here. So, this is pKa2 and this is pKa3. So, our pi for lysine will be an average of pKa2 and pKa3. We determined pKa2 as roughly 9 and pKa3 as somewhere around 10.2. So, the pi of lysine will be average of 9 and 10.2. Okay. So, that is all for week 2. Thank you. We will see you in the next week.